for sound. Do you have sound? Check, 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 sound. Good. Sound, check, 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 check. Check, check, sound, sound. Yes? No? Sound? Sound, sound? Good? Sound? Okay, let's switch. My suspicion is that what kills the resolution or causes the shift is I have run the some of these apps and simulations on the tablet itself, and maybe switching between the tablet resolution and the computer resolution is what kind of is causing that to oopsie. Okay, so switch. How's that look? Does it look good going out? Yeah. Okay. Cool. Are we live? Live from Berkeley, California. We need the voiceover announcer. It's Chemistry 1A with your host, Mark Kubinec. Hello, everybody. Welcome. Those in here, those out there. To Chem 1. We've been talking about gases and the behavior of gases. This is kind of a break almost, I think, from the intense mathematical stuff that we were doing before this. We're going to ratchet it up a little today. But again, we're going to look at some math that we are going to explain with pictures and plots. So focus on the result, the picture and the plot, and what those things mean. So we talked about the ideal gas equation, and we had the three state variables: the pressure, the volume, and the temperature in Kelvin, as well as the extent of the gas, the number of moles, the number of particles. Importantly, this new constant, also R, unfortunately. So we used R for Rydberg's and we're using R for the gas constant. So keep those sorted. And the temperature, absolute temperature in Kelvin. And we talked about last time the range of temperatures that are noticeable, that can be achieved in the universe, the interior of suns, stars, and the Bose-Einstein condensate, a few billionths of a degree within a few billionths of a degree of absolute zero. So in that case, and we know absolute zero, all motion would stop. So we can't get there, but the Bose-Einstein condensate, all matter if you do the matter with bosons, if your matter is bosons, those are allowed to collapse into the same quantum state. They can have the same quantum numbers. There are basically the two types of particles in physics: the boson, which is an integer spin particle, and this spin is the same kind of thing we've been talking about with the spin of the electron, plus 1/2, minus 1/2. If your spin is plus 1, minus 1, then you also usually have 0 in there, then you're a boson, an integer spin, and the quantum numbers can overlap. And that means spatially you can overlap in space. And it's one of those predictions from quantum mechanics that Bose and Einstein proposed in 1918, maybe ish, somewhere in that range. So 1920s, but not realized, not actually made. So predicted, but not actually made until the 1990s, and a Nobel Prize was awarded for that. And we reminded ourselves that when a system radiates, the temperature is given by a perfect radiator, or it's often called a black body. You'll see those two things used interchangeably. And we can look at those again. So here is a nice plot, and we'll go to the screen. We have good resolution. So here I can adjust the temperature, and I can look. So what I'm looking at here is the distribution of intensities along various wavelengths. And those vary with the temperature. So if something is around 5,000 degrees Kelvin, there's a peak right in the middle of the visible wavelengths. So you have them from 400 to 700 nanometers. So something around 5,000-ish degrees, 6,000 degrees begins to look white, hot, because you see all the colors. And as you get hotter, you can see that peak in intensity of the radiation being emitted. So all these wavelengths are still being emitted, but the peak moves towards the ultraviolet. And now we're at 7,000 degrees. When we get up here, 10,000 degrees-ish, we're going to, that peak is going to go right out of the visible spectrum. I'll bring the y-axis down. Whoops. Down so you can see it. So the intensity's gone way up, but now these are emitting in the ultraviolet, and our eyes aren't sensitive to them anymore. The shape of this curve, we haven't talked about it a lot, but the fact that this drops off here is what inspired Max Planck to come up with the quantization of energy and the photon scale. So that's kind of an interesting applet to look at. That's in your notes if you want to look at those. So we can go back to the PowerPoint here. And we talked about this Bose-Einstein condensate being matter all on top of each other. And I told you the story, so I went back. I told you the story of archery. And if you know the story of Robin Hood, you may know that in the archery contest that the Sheriff of Nottingham put on to capture Robin Hood, Robin Hood had to win the competition by, there was a very good shot right in the middle. His shot split the arrow that was already in the bullseye. So here, this is happening. And I bring this up because it emphasizes accuracy and precision, which is something you should understand in as a scientist. There's a difference between accuracy and precision, and we make that distinction in science. And in archery, it is a very famous example where accuracy and precision come hand in hand. So precision is the ability to reproduce an experiment and get the same number every time. So this is the ultimate in precision when you split one arrow with another arrow. But all of these arrows are precise. They're all very close together. And that's what you shoot for in archery. You don't really care when you're practicing where the arrows go on the target, as long as they're all going in the same place. So precision is your goal. That means you're doing everything exactly the same every time. Accuracy would be if they were in the center, the actual value. So if you're getting measurements and the actual value of the parameter, then that's an accurate measurement. But you can have accuracy without precision. You could have measurements all about the center, but the average, if you're taking the average of all your measurements, is still the established number. So you can have accuracy without precision. And of course, if all of them are stacked together on the exact bullseye, that's accuracy and precision. And so I have on my phone, I have the box ticked that says keep messages forever. So I was able to go back and find the message. So when I did this, I said to my colleague, this would make a great accuracy and precision demo. I'll just bring the bow to Pimentel and shoot in Pimentel. And then he said, oh, arrows are bosons? Because he noticed the arrows were able to overlap in space. So here's how ginormous a geek I am, and maybe my friend, I won't speak for him, but I of course said, well, that depends on your budget. If you buy the fermion arrows, then they never do this. They never overlap in space and they last longer. And then the Pauli principle ultimately excludes precision. That is, you can never do this if your arrows are fermions. And the Pauli exclusion principle that says you cannot have the same quantum numbers applies to fermions. And that's most of the matter that's important, especially the electrons. So Pauli exclusion principle ultimately is what prevents things from coming all the way together and on top of each other. You could think of it as responsible for the hardness of matter. So even though we know the atoms are mostly empty space, and we talked about that the first day of class, we understand now quantum mechanically they don't overlap, even though there's all that empty space, because they are fermion electrons and they cannot occupy the same set of quantum numbers. They can't have the same place in space. And you see I did the play on words. Pauli excludes precision. We are huge nerds. So let's do a chem quiz based on that. Not that principle, but what we've been talking about, getting back to the gases themselves. So an ideal gas is in a 1 liter balloon. And you have these conditions, a 1 liter balloon at 1 atmosphere of pressure inside that balloon and outside the balloon to a certain extent. That's what's holding the balloon at 1 atmosphere. Some of it's the tension of the balloon, but also the gases outside are hitting the balloon. So gases inside striking the surface, creating pressure, gases outside, balancing that to a great extent. And it's pretty hot. It's at 100 degrees Celsius, boiling point of water. I'm going to heat it more to 200 degrees Celsius. What's the final volume of the balloon? Everything else stays the same. So we'll start the chem quiz. We'll go to our breakout rooms. We're in our breakout rooms. And when that responds, a poll will begin. And let's talk about it. Okay, we'll come back together. Had a good discussion in the breakout room. Everybody had just woken up, but they still, I didn't really consider that this 8 in the morning, that not only do you have to get up, you have to be sharp, and a lot of people aren't morning people. So getting up, talking to other people about science when you're groggy. Let's see how you did with that. Many of us think A, many of us think B. But A, the most popular, saying the change would be a bit less than 2 liters, not 2 liters. And this question is to emphasize that that temperature appeared to double, but everybody was doing the right thing. The volume of the gas, we can just say PV equals nRT in the initial conditions and PV equals nRT in the final conditions. And then what stayed constant, the P and the N go out, the V and the T are left. And you can solve for the final volume. It's the ratio of the temperatures. And you have to be careful. That looks like the temperature doubled, but that is not the temperature. The temperature is absolute temperature from 373 to 473, and that's not quite a doubling of temperature. So that's just to remind you, wake up call, not just literally this morning, but wake up call for your homework and the exams. Temperatures are in absolute value, the absolute values, the Kelvin scale. So here's isothermal combustion. And again, hydrocarbon burning in oxygen makes carbon dioxide and water. A mixture of an atmosphere of methane and 2 atmospheres of oxygen react. According to this balanced chemical equation, what happens to the total pressure? They react completely. Oh, I guess I shoot. Well, I'll talk it through because maybe I'm giving some of this away. Do they react completely? What you need to do is figure out how many moles of gas are left after the reaction goes. So part of this, maybe I gave part of it away, is you have to check how far towards completion the reaction goes. Is there enough methane and oxygen? Are they in the appropriate ratios to react completely? Or is there some pressure left over on the reactant side because it did not go to completion? One of those reagents limited the extent of reaction. And on your midterm coming up Monday, you'll see this again, where you have to go back to the beginning of the class and remember everything you know about stoichiometry and apply that, but this time with gases. So the moles of gases relate to their pressures and their volumes, partial pressures being the most important part of that. So if you look at this equation, you have to balance it. And after you balance it, you see that the ratio in moles is 2 to 1 methane to oxygen. So that is the appropriate ratio, molar ratio, and partial pressure ratio to react completely and give you a mole of carbon dioxide and 2 moles of water gas. So 3 moles of gas on this side, 3 moles of gas on that side. So that's the pressure is the same. What are the partial pressures? Well, you know how many moles of gas. So some of the pressure is coming from the water molecules. Some of them is coming from the carbon dioxide molecules. And you need to be able to say that the partial pressures are carbon dioxide doesn't know the water molecules are there. Every gas behaves completely independently of the other gas to a large extent, and this 1 mole exerts 1/3 of the total pressure, you could say, because there's 3 moles and it's 1 of them, or calculate PV equals nRT for that. So calculate the pressure of O2 by saying, well, it's the moles of O2, N, R, and the temperature over the volume, but this is the entire volume of the flask. So you have to say oxygen has the entire flask to work with, and water has the entire flask to work with. So the partial pressure of the water is 2 RT over V, and the total pressure is the sum of those 3 RT over V. So indeed, oxygen is 1/3 of the pressure, water is the other 2/3 of the pressure. Okay, let's do this one. A mole of sulfur atoms occupies around 22 liters at a 1/4 atmosphere of pressure and 546 Kelvin. Now that is the absolute temperature, so we can put that one in directly. What's the molecular formula of the sulfur? So we know how many sulfur atoms are in there. The question is, are they atoms, or are they some kind of molecule? 1 mole of sulfur making some number of molecules of a sulfur molecule. Let's talk about that one, and we'll take a vote. Oh, we don't have any lights. Oh, this light isn't on. I think we have to turn this light on and raise it. Oh, goodness. Raise it up without breaking. Ooh, breaking things. And I think you can actually even shine it kind of over here. Okay, am I on? Okay, you guys heard me mumbling about the lights there. Turn the mic on early. Let's see what you're thinking. Many of us think it's S2 is the formula for this. That is, there's not a mole of total particles. You're saying there's half a mole of particles because the sulfurs are in groups of 2. So that reduces the number of particles by 2. So let's see if I agree with you there. So you have to say to yourself, a mole of particles. If it were under these conditions, that would be absolutely correct. Around 22 liters, 1 atmosphere, and 273 K. That says that the 1 mole of gas, that's standard temperature and pressure for a mole of gas. But it's not. It's 22 liters, yes, but it's only a quarter atmosphere. So in that case, and now I've kept the temperature the same, that would be the same kind of reasoning. You would say, well, there must be a quarter of the number of particles. So that would say it's something like S4s, but the temperature is also twice as high. So that says I have a factor of 2 in temperature. So that should increase the pressure, but it didn't. Pressure stayed the same. So I have to decrease the number of particles. And that's about a factor of 2 as well. So the particles in there are S8 particles. I think many of you got this way, but then did the factor of 2 and went the wrong way with factor of 2. So it was this step, but that step. So you raise the temperature by a factor of 2 without changing the pressure. So something had to happen. And the only other thing you can vary is the number of particles. So you had to reduce those to maintain that same pressure. Fantastic. We are more or less on the same page. Temperature, pressure, volume coming together for us. So now we're going to, as promised, turn on the math a little bit more. Can you grab the water behind you there? Thanks, Leo. So as promised, we'll ratchet up the math a little bit. But I'm going to do this in kind of a more or less hand-wavy approach. So we're not going to get into too much detail. We've already talked about this many, many times, the microscopic origin of the pressure. The pressure comes from the particles colliding with the walls elastically, if it's a real, an ideal gas. So no energy is lost, no momentum is lost. Momentum is conserved when that collision occurs. So the particle comes in and whacks the wall. The higher momentum it has, the more pressure. The more particles hit the wall, the more pressure. So the pressure comes from these collisions, and the pressure is going to be a function of the volume, we know, certainly the number of particles. The more that hit the wall, the higher the pressure. The massive particles, if they're more massive at a given velocity, they impart more momentum, so higher mass. Higher velocities of the particles would also give you higher momentum. So all those things factor into the microscopic origin of the pressure. So we can look at it in terms of the physics. So you transfer momentum from the particle to the wall. And if the particle comes in with a momentum, and remember the formula for momentum is mass times volume, mass times velocity. It's a vector quantity. It has direction. And this one has direction in general towards the wall. And it leaves with something like the opposite of that momentum. Opposite because the velocity has the opposite sign now. It's going in the other direction. But momentum is conserved. So how did I get a particle going from plus mv to minus mv? That's a factor of 2 mv. I went from plus mv to 0 to minus mv. That's a factor of 2 times the momentum. So that is what is transferred to the wall in that collision. So something like 2 times the momentum of the particles. And again, this is a little hand wavy, partially because what angle did they come in and a few other things. But we're going to kind of account for those. Well, we're going to account for them exactly, but not do all the math. So that's part of it. How many, the kind of the energy, the momentum transfer of the collisions, times how many collisions. So the collisions per second and per unit area. So the number of collisions goes as how fast they're going in general and how many of them there are there. So the frequency of the collisions has that factor, the number of particles and how fast they're going. But we divide that by the volume because the particles are spread out all over, and pressure is force per unit area. So we have to concentrate on just one area, and many of the particles are going somewhere else. So we divide by the volume to divide the particles up over the whole volume. And you can see that would give you units of area too, because this has meters per second and that has cubic meters. So that gives you one of the meters cancel and you'll have per unit area if you look at that. So that's the frequency of the collisions per unit area about, and that's what these squiggly signs mean. We haven't done all the math. So let's multiply those two things together. So the pressure goes as, that's what the squiggly means, the number of particles, their mass and velocities. Two factors of the velocities come in, one from the frequency of the collisions and one from their momentum, divided by the volume. And once we're there, we average over all the velocities. And we're going to average over the velocity squared because we're there. There's two factors of the velocity there. So we average over all velocities, and that's what this little bar means. So the mean square velocity. And now I'm going to call it a speed. And I'm going to call the speed. Speed is the magnitude, but not the direction anymore. So it's the magnitude of the velocities. And we're actually doing something here that something like we did in quantum mechanics. Some of the velocities are positive and some of them are negative. And if we were to take all of that, we wouldn't get, we could say, well, you have 0 net collisions on the wall. We take the square of the velocities there, and then this factor of 3 comes in because we're talking about speeds now, and there's 3 dimensions they can travel, and only a third of them are going at the wall. So we kind of divide that by 3. And then this is precise. So I now have the equal sign. The number of particles, the mass times their mean velocity squared, divided by 3 times the volume. So that is a derivation, a relatively simple one, of the microscopic origin of pressure. So now we understand how the particles, the property of the particles, and you probably recognize that, mv squared. That looks like the kinetic energy already of the particles is responsible for the pressure. So let's explore that idea a little more. We'll do a little more, a few more manipulations. So here's that expression, and we're interested in the temperature, which we don't see in there yet, and we know that goes as the energy of the particles. We kind of see the energy in there. Well, let's write it so the energy is in there. Let's pull out a 2/3 and put in a 1/2. So just do a very simple mathematical relationship. That 2/3 hits that 1/2 and makes the 1 that's here. But that now is the kinetic energy of the particles. So now we see the pressure volume product is coming from the kinetic energy of the particles. And if you take nothing else home from Chem 1, that's all the energy they have, and that's only a function of temperature. So now the temperature is in there. So that equals RT still, PV equals RT. Just we're talking about a mole of gas, 1 mole and 0 particles of gas. But now I don't like that 2/3. I'm going to multiply the whole thing by 3/2. And now I just have the molar energy. This is the energy here per particle, the individual masses and the average speeds times a mole of particles. So that is, oh my God, that is the kinetic energy of the sample, a mole of particles, equals what we've been saying the whole time, 3/2 RT. So we've derived from our understanding of the particles smashing into the wall, measuring the pressure volume, seeing that that's related to the temperature, and energy temperature relationship arises from that. And if you look at just this little bitty part without the N0, so this is the energy per mole, this would be the average energy per particle. I'll just give it the little e, lowercase e. And average, because that's you're using the mean square speed to get that. And that's, we'd have to divide through by N0. We'd have to divide through by Avogadro's number to get this. So if you divide this side through by Avogadro's number, you have R over N here. I'll just write that down. If you divide through by Avogadro's number to get just this quantity, then on this side, you have divided by Avogadro's number. That is the energy per particle, the average energy per particle. So this quantity here, R over N0, is that constant there. And that's the Boltzmann constant. So Boltzmann constant is the gas constant per particle. R divided by Avogadro's number. So we'll just write that down. The value of the Boltzmann constant is this ridiculously small number. And it's called Boltzmann's constant. We've seen it before. And it is the gas constant divided by Avogadro's number. So we've reached a kind of interesting place. We've come another full circle where remember the last time we used Boltzmann's constant? No, not at all. I know the answer. We could do a quiz. It would be no. We did use it when we talked about the entropy of the system being related to the natural log of the number of ways, the microstates. And this is the same Boltzmann, okay? So Maxwell-Boltzmann was interested in statistics, and this is a statistical argument. You're taking the mean of the velocities of the everything in the sample. So there's a distribution of velocities, and he's doing statistics there. And that spread of energies, the number of ways to arrange the system, occurred to Boltzmann as well. So that's a nice, neat little tidy package to take home. So let's do a chem quiz related to that. We'll just talk through this one. This is a very important concept. This is going to be on your exam, this concept, because it's one of the most fundamental concepts to come out of our whole this is called kinetic molecular theory that we're doing. Boltzmann statistics of a gas, Maxwell-Boltzmann statistics of the gas. So I think I called him Maxwell-Boltzmann. Sorry, just Boltzmann. They're two different guys. Oops, let's look at that. 1 mole of bromine and hydrogen are in this balloon. They're the relative molar masses over there. We know them. Hydrogen 1, bromine 80. What are their relative kinetic energies? So how do we go through this? Well, we have to think to ourselves, the partial pressure from each of those, 1 mole of each of them, or equimolar amounts, each of them are responsible for half the pressure. They don't know the other one is there. Each are exerting the same pressure, even though they have different masses. They each have the same energy because they're gases, and the only thing that affects the energy of the gas is the temperature and the extent. More gas is more energy, more particles, but it's 3/2 nRT. 3/2 RT is the energy for 1 mole of gas. So they each have 3/2 RT energy in there that there is being bombarding the sides of the balloon and causing that pressure. But if they both have the same energy, they both have, that only depends on temperature, so both of them have the same average kinetic energy. The energies of the particles are the same. The kinetic energies of the particles are the same averaged over all the particles. This is the molar kinetic energy. It's the mean squared velocities. The kinetic energies of those two gases are the same. So that begs the question, well, if the kinetic energies are the same for the bromine and the hydrogen, the bromine is so much more massive than the hydrogen. There's that huge difference. But if these are going to be the same, the mv squared is going to be the same, the very small mass for the hydrogens must mean they are going much faster to get this quantity to be the same. And the very massive bromine on average are going slower. So there's this distribution that Boltzmann was thinking about, distribution of velocities. And on average, the hydrogens are going fast and the bromines are going slow. They have a different distribution of velocities, same pressure exerted by the same number of particles at the temperature. Their energy is fixed by that. So let's look at those velocities. I do want to know what the average velocities are. I do want to plot out that distribution of velocities. I know there's a lot of them. What are they? So let's start to get there. First, let's get an expression for the velocity. So the energy is 1/2 the mean squared velocity. There's the energy per particle, if I use Boltzmann constant. So I'm going to say, well, I want the velocity, average velocity of the particles. How do I get it out of there? Well, that's the mean velocity squared. Let's take the square root of that to get the mean velocity. So we're going to take the root mean squared velocity, the square root of the mean squared. And that's the kind of thing, again, we do. If we want to know the magnitude of something, square it and then take the square root. Square it to get rid of all the signs going every which direction, and then take the square root to get the magnitude. So root mean squared is the square root of the mean squared velocity. And that we can solve directly from those relationships. Just solve for the mean velocity squared and take the square root of it. So that's my phone. I'm not far enough away to turn it off. about that. So I can do it per particle or per mole. So m, the molar mass, m, the mass of a mole, m, the mass of the particle, the tiny, tiny mass of the particle, that's the molar mass for the total energy, average energy of the system. So the root mean squared velocity is affected by the temperature, of course, higher temperature, higher energy, and the velocity of the particles is affected by the mass, heavier particle, lower velocity. Relatively straightforward, so we get the average speed of the particles. Not exactly the average speed, the root mean squared speed. So we'll talk about this one together as well, because this is relatively dull. One of the students the other day said, well, I think I see the obvious answer, so that must not be it. In a sense, it's all these answers are the obvious answer, but you have to think about it exactly right, and your initial impressions are often wrong, so you have to come back and think about it scientifically. A great mathematician here at Berkeley, a student came in with his book, and he said, well, here in this book, you're doing this proof, and then you say, and it's obvious that, and he went from one step to the other in the proof, it's obvious that this leads to this. And the student said, what do you mean by that? And the professor, who had written the book decades ago, of course, wasn't thinking, looked at it as well. And then he said, hold on a minute. He went into his office, came back an hour later, the student stayed, and he said, yeah, it's obvious. It took him an hour to go back and realize it was obvious. So the idea here, this one is, I think, obvious. If you're going to plot VRMS versus X and get a straight line, you have to plot versus the square root of t. And the slope will be 1 over the square root of m. Okay? So this slope has the mass in it, and that line, root mean squared velocity versus the square root of t, would give you a straight line. Okay, we're there. Let's get there. Let's look at the distribution of speeds. We've got this root mean squared. We know where the average is. So the distribution of speeds, so if you take the number of particles which have a given speed, so all the particles with this speed, all the particles with that speed, all the particles with that speed, we already know if we average them all up, we get this root mean squared speed. But what does the distribution look like? Well, they look like this. And again, the functional form of this, if you want to write the math out, an achievement of outstanding erudition and brilliance to derive this, the expression for this distribution of speeds. That is, we can write, now we can just apply our general statistics. We know the average of this distribution, and it tails, there's a lot of particles out here. It tails down here. Like if your midterm averages, if there were a lot of low scores, the average wouldn't be here at this peak. It would be off here. So that's the average velocity. The root mean squared actually is even farther down the curve. It's still predictive of the shape of the curve, but just it's, and you could go through the mathematics and show that the root mean squared is less than the average speeds. But we're just going to notice it's the case and remember that that's the case. The functional form, so the famous functional form, and you do not need to know all this expression exactly. The result, the curve, is what we want you to know, but I'm going to write it down because it helps us understand the curve a little bit. There's a bunch of constants. Boltzmann's constant, the mass of the particles, pi. Amazing where pi comes in, and the temperature. Pi comes into nature. Just Google that someday. Pi coming into nature. Places where you would not believe it comes in. It just baffles the mind when somebody says, what keeps you up at night? What do you think about? I think about, why does pi come in? Pi actually comes into the random collisions of a wall of random numbers of particles. Pi. It does. Weird. So there's this term then. Now that term has the speeds in it, the speed squared. And this term, which is an exponential term, which has the kinetic energies over the temperature. So E exponential minus EA over RT or KT for a particle. And we want to know the individual particles here. So we have to use the Boltzmann constant. So that is rather crazy looking, but the two parts of it help us understand. There's this part that's just the velocity squared. That curve we know, that's just y equals x squared. And this part here is the exponential part. We know what exponential functions look like as well. So the product of those two functions gives us this. That means, and we can, oh, for goodness sakes, did I close the browser? Oh, goodness. No, I didn't. I'm just in full screen, I guess. See if I can get out of full screen. There's the browser. So we will go in our browser to the Maxwell-Boltzmann distribution. And here this is, do we still have high res? So here this is, so come to me for a second. So here is the generic expression. It's got rid of all those constants are now in A. X squared, which is the velocities, the speeds, exponential x squared over b. And now x squared is there because it's the energy over the temperature, and the energy has the velocity squared in it. So this is the general form of that. And it comes from two things that we understand. Here in blue is, and you can go back to the board itself. Here in blue is just y equals x squared. That means that the curve has to go to 0. Because the overall Maxwell-Boltzmann distribution, the x squared term, the speed squared term, when the speed is 0, that function is 0. And then there's the exponential portion. So the product of those two gives you the curve shape that we see here. And this is a neat little gizmo because you can change the magnitude of the constants. So there I made A larger. So as we know, A had the mass of the particles in it. So that's a more massive particle. And you can see how that changed the distribution. Sucked it back in like this. B has the temperature in it. So increasing the temperature shoves that curve out as well. The product of that exponential and that quadratic give you the curve. And you can see if I go to higher temperatures, I get the curve expanding. I get a larger distribution of speeds. And that might make some sense. Higher temperature, greater distribution of speeds, more speeds available to the system, more microstates available to the system. That's what Boltzmann was thinking. And if I increase the mass of the particle, so I go to a massive particle and that squeezes the distribution back together because this curve, the quadratic part, comes into play. So that's a beautiful simple mathematic thing. And again, these things you can play with. They're in your notes. So as we saw, if this curve, this blue curve, represents low temperature and high mass squeezed together here, those two factors squeeze the curve together. And of course, the amplitude has to increase because the number of particles is the same. So the area under the curve can't change. Total number of particles is the same. If I go to either a higher temperature or a lower mass, or both, of course, the curve, the distribution goes a greater distribution of speeds. So I have more speeds available, more microstates available at lower mass or higher temperature. And of course, there's still a most probable speed, the very top of the curve. That's the one where the most particles have that speed, but there's the root mean squared. So the root mean squared velocity on average going to higher temperature or lower mass, the speeds increase. The average speeds increase. So those shapes are what you need to look at and understand. And I have to do that thing. We can look at that if I have the properties of the gases. So here I have a bunch of gases. So I have this system here, and I can put gas into this system, and I can measure the pressure and the temperature. So I'm going to shoot some heavy, the blue particles, I'm going to shoot a bunch in there. So 2 pumps, they're the particles. And they have a distribution of speeds. Now here they start interacting with each other. They're causing the pressure to increase. You can see that pressure increasing, and go back and forth to me as you see fit here, Sydney. So the pressure is stabilizing at about 12 atmospheres. And you can see some particles moving slowly, some particles moving a little faster. I can warm the system up, put a flame on it, and the temperature is going crazy. There I'm doubling the temperature. And of course, the pressure increased. We understand that. But the distribution of velocities changed. Now you have particles with higher velocities. More microstates are available. I can go to higher velocities. Still some particles that are almost stopped in there. So there are some with very low velocity. There's a distribution. Let's put some light particles in there. Now you can see, I think, just visibly, the distribution of velocities for the lighter particles is bigger. You have some at much higher velocities, still some going very slow. So that curve, way on me? Brilliant. That curve got wider, same area, so the amplitude came down, and that Maxwell-Boltzmann distribution is there. In fact, we can look at it. Let's plot the energy. So let's squirt those particles in there again. Injection temperature, let's make it kind of hot, 550 K. Let's take the particles and just squirt the, I don't want to make the math too hard, I might crash the computer. So here I'm looking at the hot particles exerting 20 atmospheres. Here are the number of particles with various speeds, and I'll overlay that plot so you can see the average looking like, or this curve, if you look at it over time, looks like a Maxwell-Boltzmann distribution there. Let's put, how many particles can we put in? Can we get some more resolution there? So now you can see that's starting to look like a Maxwell-Boltzmann distribution. And we can put that envelope there. That looks like a Maxwell-Boltzmann distribution of speeds. You put in, I'm anxious. All this, this is done locally, so my computer is having to do all this simulation. I don't want to crash my computer, but I'm going to throw some of the heavy particles in there. And now there's the two distributions of the heavy particles, and you can see the heavy particles overall slower. And I'll do that same thing. I'll overlay onto that the distribution of the blue particles, the heavy ones, and the distribution of the red particles, the light ones. I think you can see that happening there. Okay, you can play with these things. Heat them up. Let's heat it up. Gonna put that, and what do we expect to see? Well, higher velocities, and look at those curves go to a higher average root mean squared velocity. The peak is now somewhere out here, and our VRMS is out here. Okay, so play with these. They're in your notes, and we got the notes. I'm sorry, there were a bunch of older notes from a previous semester on there. Those are all updated, so you'll have these links if you download the notes pages. Okay, so let's look at this in particular. Here's the Maxwell-Boltzmann distribution at around 300K for bromine and something else. So bromine is the blue one. The something else is the X one. What is X? And I have a scale now. Often we don't have scale. It's all qualitative. But here there's some quantitative information about those RMS speeds. So let's think about that together in your breakout rooms, and we'll take a vote. Boy, those batteries do not last very long. You have to charge them every day. Sorry. I should not turn my mic on when I'm muttering about the lighting in the room. Take this opportunity to vote if you have not yet voted for this one, and we'll see what you're thinking. I don't want to. We'll see what you're thinking. Many of us think argon, BR2. Oh, it's BR2. We were just talking about it. It's not bromine atoms, it's bromine molecules. We just did the whole thing in our breakout room. We did bromine atoms. Oops. The B people did bromine molecules, and they came up with the right answer. So let's look at that. Stop that, make that go away. Let's talk through it. It looks like you guys have the right idea here. So that was quantitative information. So bromine molecules and X particles, whatever the heck they are. And these particles, bromine makes atoms, but the diatomic molecules, the neon and the argon are the noble gases, and they are the atoms. So those don't pair up as molecules, as we know from our molecular orbital theory. So this is a factor of 2. So this thing, X, has twice the root mean squared velocity as bromine at the same temperature. So if they're both at 300 K, the RMS velocity goes as the temperature, square root temperature, which is going to be the same. The mass, so what do we have to change? By what factor do we have to change the molar mass to get a factor of 2 in the RMS speed? Well, we have to have a factor of 4 in there because of this square root. Okay, so that factor of 4 would come up into the numerator, divide the denominator up in the numerator, take the square root, and you'd have that factor of 2. So it's 1/4 of the mass of Br2. Br2 is 160. 1/4 of that are the argon particles. Absolutely. I like it. And like I said, we were talking about it quickly in our breakout room, and we just neglected to do bromine molecules. We said bromine atoms. So clearly, even me looking back at these, I go through them quickly and don't come up with the right answer either. That's not the point. The point is to think about it. All our thinking was the same, except the trivial part of the mass. So let's calculate an actual number. What is the RMS velocity of that bromine at 300 K? What is the number? Well, we can get the number. We'll talk about this together. So if I have bromine trapped in a flask here, I open the flask and let it go flying to the other side, and you know it will. It'll flying over there. How fast does it travel across that? How fast on average are those particles going? And this flask was evacuated. So those particles go flying over there with nothing in the way. And you understand, that's why things expand. We've been talking about expanding against a vacuum all the time. And we said, oh yeah, of course it expands because the particles have high velocities. Now we can figure out what they are. And the particles that have the velocity going in that direction go flying over to the other side of that flask. And statistically, at the end, you have equal amounts in each side. Boltzmann would tell us, and our study of entropy told us that's the most probable distribution in the end of particles over space. The distribution of velocities, well, we can do that. We have a simple expression for the root mean squared velocity. It's 3RT over m. We said it's around 300 K. So I put in, I don't have the units here, but I have the 3, the value of R, the absolute temperature, and the molar mass of the bromine. And I've changed the molar mass to kilograms. Don't put the molar mass in grams in there. R is in joules, that's kilograms, meters, seconds. I have to use kilograms, meters, and seconds if I'm going to use R in joules. So that's a point of slip up. Be careful, you get temperatures in Kelvin and masses in kilograms, and that is around closest to 100 meters per second. So very fast, 100 meters per second. What's the fastest person? The fastest Usain Bolt 100 meters is around 10 seconds. So he's not going 100 meters per second. He's going about a meter per second. 10 meters per second. So that's the Usain Bolt human speed. Here's the speed of the gas particles. So the gas particles are going 300 meters per second on average, and they're smacking into us. So we are in tune to those collisions, and they're on average going very fast. It turns out, though, even though they're going very fast, they don't move very far in space. And we saw that in our distribution. Even though they're going fast, they keep colliding with other particles. So in terms of moving that 100 meters, moving across a football field, even though they have this high speed, it's a velocity, so it's going in all directions, and there's the collisions, and it takes hours, hundreds of hours for a bromine, if you could track one, to make it, and maybe never statistically make it 100 meters across a football field. So there's that diffusion aspect as well. Interesting, though, how if I were going to race, or Usain Bolt would be better, if he was going to race the bromine across on a 100-meter tube, so you had Usain Bolt and your bromine locked up, vacuated tube, and you're going to race, of course, Usain's going to get creamed. But could we bring the temperature of the bromine down so it's fair? How far do we have to bring the temperature down? Well, we have to bring the temperature down. It goes as the square root of the temperature. So we want to get this from around 100 to around 10. So we have to bring the temperature down by that square root of that difference. So a temperature of around 30 Kelvin, we'd have a chance at racing the bromine across that 100-meter field. That's cold. Of course, we know 30 Kelvin, nitrogen is frozen. The air would be liquid. Nitrogen frozen. I don't know where it freezes. It boils at around 70, 77. The air would be liquid. Okay. So let's continue now. These have been ideal gases that we've talked about in detail. Let's add real properties back. And the major real property that we add back is interactions between the particles. So now there'll be intermolecular forces that we add back. So we can say, if we take a real gas, we've done this, we plot pressure versus volume for a given temperature. If we decrease the volume, so I've gone down in volume here, squeeze that, the pressure goes up. So we have that from the ideal gas law. Here I'm going to plot it for a real gas. I'm going to drop that volume, the pressure goes up. Okay, same thing. Because the gas is behaving ideally, and most gases at dilute gases, so low density gases, behave ideally at room temperature. Let's keep going. Squeeze this again. Pressure continues to go up, and we know the shape of that curve. That's P times V is a constant. Let's squeeze this guy again. A crazy thing can happen. There, I squeezed, but if I was plotting it for a real gas, just measuring the pressure, I have my little pressure gauge here, reduce the volume, the pressure gauge did not change. So something's happening in the real gas. And I know the temperature didn't change, the volume did change, but the pressure did not. So what had to change? The number of particles. So some of the gas particles went away. They can't escape. What happens? I think you know. Some of those gas particles go into the liquid phase. So I just lose the number of, I get a lower number of particles. That allows me to go to a lower volume at the same pressure. So the behavior here now is P times V is, I don't know. How do we get that to happen? That slope flattened on us. And we can do it one more time. Squeeze hard here. Now if I squeeze hard here and the pressure goes up very dramatically and try to squeeze one more time, now we know you're squeezing a liquid and the pressure is going to go up very dramatically. We don't know the equation of that line very well. We know the equation of this line, P times V is a constant, and then it starts doing weird stuff on us. So something happened in there. What happened? Condensation occurred. So you could think of it two ways. If you were to change the temperature, that condensation would occur as well. So you change the temperature and the particles all condense. That would be a dramatic reduce in pressure, that all those particles condensing. You could do it with temperature as well as volume. So you'd get that same dramatic change in pressure if there was a temperature change or a volume change. Lonnie can do it with the pressure. So we'll look, with the temperature. Temperature is easy to do. So we'll do the temperature. Volume's easy to do too. But here, we'll go watch Lonnie. Lonnie's going to take gaseous water in 2 soda cans. So he's got the soda cans on the burner and a little bit of water in each, covered. So it's gaseous water in each of them. And he's going to take the can. Oh, first he's going to squirt it to ensure there's gaseous water in there. So a little water in there, a little water in there. He already had them boiling, so there's gaseous water. Just make sure there's enough. Let them heat up. He has an ice bath here. So he can dramatically change the temperature, and the condensation will lower the number of particles. And look at that. The number of particles decreased dramatically. That decreased the pressure inside dramatically and crushed the can. What crushed the can? That just tells you how hard the particles on the outside are actually hitting the can. The only reason it didn't crush before is there were the same number outside pushing back. You take those particles away, and yeah, that 300 meters per second starts to matter and just destroys the can. So a beautiful demonstration of the actual pressure. And again, that is nothing, that's not anything happening inside the can per se. The vacuum does not suck the can in. So you're losing particles, you're going to a vacuum inside the can. Vacuums do not suck. That's not suction. There's no such thing as suction. I don't even know why we have that word. What happens is the particles outside crush it, is what happens. They always do that wrong in sci-fi movies too, as well. So you're in space, and you know there's a vacuum outside. You have a pressurized spaceship. The hull is breached, and people go flying out the hole. They are not sucked into space. Space does nothing. It's a vacuum. What shoots them out into space are all the particles rushing out and carrying them out them with the breeze. So it's the pressure inside rushing out that causes, so you're not sucked into space, you're blown into space. Don't do either. Okay, so here I do change the temperature, and we've seen this already. The isotherm, PV is a constant, the temperature is a constant. If I change the constant by changing the temperature, then the nature, when that change, the plot changes appropriately. So these are higher temperatures. These are higher isotherms. So if you go to higher temperature, you get a different same shape, PV equals a constant, but a different position in PV space. What about over here? If you increase the temperature, so here's a T1 isotherm here. This I've labeled TC, the critical temperature. I'm going to go higher than that, and when I go above the critical temperature, look what happens. The gas behaves ideally again. So there is a temperature. If you get high enough, the gas behaves ideally. All that happens is the density just increases. P times V is a constant, smaller V, same number of particles, the density smoothly increases. Here, the density didn't smoothly increase. So the point where that real behavior just disappears is called the critical temperature. Above the critical temperature, a gas behaves ideally. You could say it continues to get more and more and more dense, but there is not a phase change. That's the interesting thing. Here, there was a condensation, and you see two phases. Here, you can get just as dense. So you can get just as dense as this liquid, but the particles are still filling the entire container. They're still behaving like a gas. So you have a very, very, very dense gas filling the container. Here, you could see two phases, a puddle of water on the bottom and the gas on top of it. Above the critical temperature, it just gets more and more and more and more dense, but fills the container. So we can modify the ideal gas law to account for this behavior. And we modify it. This is called the van der Waals equation. So the ideal gas law modified to account for real behavior. So there are two terms here. There's a term here. The number of particles are there. A is a factor that adjusts the pressure. It makes the pressure change. And that accounts for the fact that there are attractions between the particles. So the particles tend to want to stay together. If you have a big enough kinetic energy, they don't. But that accounts for, A accounts for the fact that, well, real particles do have a tendency to stay together if they don't have enough kinetic energy. That is what condensation is. Don't have enough kinetic energy, so you stick together and there's a phase change. A accounts for that. This term B adjusts for the fact that the particles have volume. Remember, our ideal gas is no interactions, volume is negligible of the particles. We put those factors back and we get a real gas law. And here's just some values of those A and B constants in the van der Waals expression. So you can see they're quite wildly different. The B term doesn't change that much because the particles are all tiny and they don't contribute very much to the volume. The A term that's accounting for the interactions changes dramatically. And look, for water, it's the largest in this list. That represents water having the greatest attractions. So the greatest potential energy contribution comes from water molecule, or is seen in water molecules in that table. So we can look at that in some detail. We'll just skip this one altogether. Not particularly interesting. Oh, and this is going to take some it's going to take some thought to work through that, so we'll do that next time. Okay, we're about 9:30. We'll wrap it up here. Cue the band. They'll play us off. See you tomorrow night. Same bat time, same bat channel. Goodbye from Berkeley.